So in the last class I started discussing about advanced spectroscopic technique, and I elaborated you on the different basic principles which are used for these techniques. To remind you that we normally use these techniques for spectroscopic analysis of different inorganic and organic compounds. So whenever an isolated molecule, suppose, is subjected to any kind of radiations and it is excited from a state, suppose if I write it properly, E1 to E2, it undergoes transition by application of any kind of radiation, does not matter what is the wavelength of the radiation. And in such a case the molecule or the species rather will come back from the high energy state E2 to U1 by emitting certain radiation. And if we know what is this frequency of the radiation, we can relate this as this one, like this. That means the emitted energy of the radiation H nu is equal to the modulus of E1 minus E2, right. So therefore I can always write this one as Hc mu bar equal to mod U1 minus E2. So where mu bar is nothing but the inverse of frequency, that is C by lambda, sorry 1 by lambda, and that means it can be written as Hc by lambda equal to mod U1 minus E2. So therefore depending on the type of interactions the radiation will have on the molecule, on the species, we can either have absorptions or we can have otherwise what is known as the emission. So either we can have absorption spectroscopy or emission spectroscopy. Now depending on the kind of energy levels, if U1 suppose is greater than E2, then we will have absorption. That means if the molecule is going to the higher energy state to lower energy state by absorbing certain amount of energy, then it is absorption. On the other hand, that means this is absorption. On the other hand, if the molecule is going to higher energy state from the lower energy state by absorbing the radiation and it comes back, that is if E1 is less than E2, we call it emission. So we can measure the spectroscopic measurement we can do either in absorption state or in emission states. That is the way normally the spectroscopic techniques are done. Now the kind of radiation which will be emitted from the absorbed by the species will be depending on the what is the input radiation we are applying. So therefore depending on input radiations different kind of situations is possible. I have shown this slide in the last class, I am showing you again. If we have suppose very high frequency like 10 to the power 6, 10 to the power 8, or rather we can have, if we have radio frequency like wavelength starting from 10 meter to 100 centimeter, we will have normally change of electronics, change of nuclear spin, okay, can be changed. Nothing will happen to this molecule or the atomic species present. On the other hand, if the energy levels are little increased from so frequency level from 10 to the power 10 to 10 to the power 12 Hertz, that is obviously corresponding to the energy level increase, that is if we go to microwave regions, and then we have change of orientation of the molecules, okay, or change of configuration of the molecule. Infrared can also lead to change of configuration of the molecule, and in the visible ultraviolet region you have change of electron distributions, or rather you can always have some kind of rotations or transition between the different electronic states which can be inclusive of the rotations. Finally, in the ultraviolet or X-ray regions transition can occur which can ionize or dissociate certain molecules, that is what is shown here in the X-ray. And if you apply very high energy, that is gamma ray, okay, or frequency to the power 18, very high frequency, then you can have change of nuclear configuration itself, like you can have the nuclear pieces can undergo transitions. So by using a host of radiation starting from radio waves to the gamma rays, one can get a large number of spectroscopic studies done. In the today's lecture, what I am going to do is we are going to analyze or look at it the most simplest one or the most widely used and the oldest technique in the spectroscopy is called UV visible. That is, if we use the radiations whose wavelengths are in the range of visible or near what is called visible but in the ultraviolet range. So, I have shown the whole spectrum starting from gamma ray to the radio frequency 10 to the power minus 10 to the power 20 rather 20 to the power 18 to 10 to the power 4 second or hertz, and UV visible comes very small 10 to the power, you can see this frequency 10 to the power 16 to the power 14, that means the wavelength would be a couple of hundreds nanometers, it will be something like 180 to 460 or 70 nanometers in that range. And visible, we know it consisting of a large number of wavelengths like red to what is called red to violet, red, orange, yellow, green, blue, indigo and violet, 7 colors are possible. Now, to give a very simplistic perspective of this ultraviolet and the UV visible spectroscopy, I will just start from a very basic thing. The obvious difference between many compounds is color. Right, to give an example, chlorophyll is what is called green. On the other hand, very complex ones like say 2,4 dry nitrophenyl hydrogen or derivatives of many alkyl ketones are basically bright yellow or kind of. On the other hand, quinine is yellow. So, these are the general difference of the color of different compounds. Now, obviously, you have already learned in your different courses that why different materials or different chemicals show different kinds of color. Well, that's basically that's how our eye perceives, our eye basically sees an object and then determine the color. Sky is blue, sun is yellow, like that. So, why it's so? Because the light reflected on the surface of any solid or basically passing through a liquid, it comes back to our eyes and we see the particular wavelength of light coming from a particular substance, and that wavelength obviously corresponding to different colors like red or maybe yellow or maybe violet in the whole visible spectrometer. This is what we know. So, that means our eye is basically a spectrometer, acting as a spectrometer. To be frank, our eye can actually distinguish different colors coming from different objects. So, it is probably the simplest spectrometer. One can always tell that eye can be of many things. It is basically a camera, it is basically a what's called phenol camera, or I can always tell that from the spectroscopic point of view, this is a spectrometer, simple spectrometer. So, and then there are many compounds which are colorless, correct, there is no color. So, that means when light falls on them, no light basically comes to our eyes in the wavelength range in the visible, so that we don't see any color. So, most important aspect will be those objects which looks colorless, they are emitting lights or emitting radiations whose wavelengths does not fall in the normal visible spectrometer, the spectrum range, like red to violet. So, they may be coming in the near ultraviolet regions, so we do not see them or we do not see their colors, we rather see them colorless. Now, when a white light consisting of all kinds of these wavelengths starting from red, different colors starting red to the violet, is passing through or basically getting reflected by any color substance, and we know that basically characteristic portions of the mixed wavelengths, all these mixed wavelengths 200 300 to maybe 600 nanometers is absorbed. Remaining portions of the light will assume the complementary color. Obviously, whatever will be absorbed will not be seen, and whatever those wavelengths will not come to our eyes. So, whatever will not be absorbed by that color substance will come back to the eyes. So we say the complementary colors. So that means we can say that if something is absorbed in the 420 to 430 nanometers, it will render yellow. Like if something absorbs light in the wavelength 500 to 520 nanometers, it will be looking red, higher wavelength reds, that we know why. That's why the red signals are used in the traffic lights, and therefore there are many so on. Okay, so early human beings actually seen these different colors, and that's how the story actually goes, and use this for decorative purposes. You know, many of these are organic minerals. In fact, we know that many stones which are used for jewelry purposes are colorful because of the color. There are many organic substances like dyes, they are also colored. So that question is now, these are all well known to all kinds of students, even the school students also they know. Question is that how can I use these concepts, as I said, this using lights to determine molecular or electronic transitions in the real what's called scientific purpose. And so that can be done, you know, by using common feature of these color compounds, whichever displays whatever I have told you is basically a system which is extensively conjugated pi electrons. You know probably the electronic structure. There are sigma bonds, pi bonds, and other bonds. So these are the pi electrons which absorb the radiations in the visible range, and that's why you see different colors. So this is all very typical of many spectroscopic techniques, and this I will discuss, and I will discuss different parts of that. Now, as I showed you that I will show you the visible spectrum in detailed manner. Ultraviolet falls in the 190 to 400 nanometers, violet is 400 to 420, indigo is 420 to 440, and red is very high wavelengths, 620 to 770 nanometers. So that means red will have very smallest frequency from ultraviolet to red. So what are the different things UV visible spectroscopy can do? Well, UV visible spectroscopy, as I said at the outset, can be used for determining the different molecular transition or electronic transition rather in the organic molecules, like outer electron binding transitions, conjugations, which we will discuss in detail, or visible ones can be used for metal or ligand study in solutions like d orbital transitions. Okay, and at the end of this lecture, if I will discuss about the instrumentation also. So to give you a better idea, UV spectroscopy is routinely used in many of these analytical chemistry labs. If you just walk in many analytical chemistry labs, people use this nowadays. In fact, in material science also, those who people study different kind of nanoparticles in solutions, we use extensively UV visible spectroscopy. And we can actually do both qualitative study and the quantitative study. Like transition metal science, we know that they show different kind of colors because of the d electron transitions, and then similarly there are many others. So solutions of transition metal science are colored. Okay, that means they absorb visible lights because electrons with these metal atoms can be excited from one electronic state to one another electronic state. That's for sure. So that because we know that the color is because of the electronic transitions from the lower energy to the higher energy. So that means we can actually determine what is the exact electronic state, and this can be basically affected by different, and then you know that these colors also can be affected by different species like different ligands. Okay, to give example, copper sulfate CuSO4 and 5H2O, this compound basically is very light blue. We know that we all of you use copper sulfate in the school days for doing experiments. If we add ammonia to it, NH3, it becomes color is more light, or rather the blueness of the copper sulfate increases, and that means there is a change in the wavelengths where the absorption maximum happens. So we can actually, if we plot the absorption versus wavelengths, A versus wavelengths, so at a very high absorption wavelength lambda max, we will see high absorption. and this lambda max will tell us the electronic tensions. Similarly, organic compounds like DNA, RNA, those have very high conjugations, absorb light in the UV region or maybe visible regions. Solvent of these determinations are often water or water solution. We know that ethanol can also be used. So that means the absorption in the ultraviolet and near ultraviolet in the visible spectroscopy region, visual wavelength region can be used to study this kind of features. And to tell you exactly the ultraviolet absorption process, let us look at that. So we know that, as I told you, there are different kinds of ball sigma 1 pi bonds. So we can have sigma from bonding orbital to the antibonding orbital, or sigma to antibonding pi orbital transitions. They are very high energy, only accessible in vacuum ultraviolet, that is when wavelengths are less than 150 nanometers, not usually absorbed in the ultraviolet visible spectroscopy. On the other hand, n to sigma star, we will discuss about n and sigma and pi in detail in a moment's time, or pi to sigma star transitions, they are actually bonding to non-bonding transitions, always star stands corresponding to non-bonding transitions, that is lone pair electrons. Normally wavelengths where this absorption is maximum falls in 150 to 250 nanometer region, or you can have like n to pi star or pi to pi star transitions, most common observed in organic molecule these transitions, and they are observed with lone pair, compound lone pair and multiple bonds, normally in a little higher wavelengths 200 to 600 nanometers. Any of these requires incoming photons to be matched in the energy, the gap corresponding to transitions from the ground state to the excited states, like from n to the pi star. Energies correspond to a one photon of 300 nanometers lights are basically 250. Now visible region of spectrum obviously corresponds to the energy levels from 36 to 72 kilocalorie per mole, right. Now in the near middle regions it will be high, so therefore energy will be near with this is visible, near visible it will be little high, so this will be approximately 143 kilocal per mole, and in that case you know this energies or the energies these are all sufficient enough to promote or excite a molecular transitions. These are very high, sufficient enough to promote this kind of transitions and observe, and so therefore we normally can use this as a transition. So to give you some even better idea, let us know that molecules have quantized energy levels from quantum mechanics. You have already studied and you know. Then you have energy and there are different energy levels, okay, and if I apply certain energies like UV or visible UV or visible range, then you can see the transitions happen from this level to this level, okay. So whenever this excited state will go back to the ground state, there will be emission, and emission will correspond to certain wavelengths. And sometimes you know each electronic levels can be thought of associated with many vibration energy levels like this. These are vibration energy levels. Within each you can see there are different vibration energy bands, okay, and they are studied in IR, infrared spectroscopy, which we will discuss after some time. And you can have rotation energy level also, electronic state can get rotated also, so therefore one can determine these transitions. So what are the natures of this absorption? Just now I told you, like one example is sigma to by pi to pi star transitions from ethylene, so at about 170, and it can be calculated actually using this software, and like this. This is the HOMO pi. HOMO means HOMO-LUMO, as you know, high occupied molecular orbital, and you can have a LUMO, lowest occupied molecular orbital, and you can see it is going from bonding molecular orbital to the anti-bonding molecular orbital, that is pi to pi star. If I apply 170 nanometer photon, these transitions can be easily detected. This is absorbed. So one can actually show that in different charts, and like you can see there pi n, then there are high anti-bonding orbitals. So you can have different transitions from pi to this pi, or pi to n, or vice versa, and then n to pi star, or you can have this type also like reversible transitions, or you can have n to pi star, others are reversible. So, all kinds of different tensions possible. This happens at lambda max of 218, this happens at lambda max of 320, and so this is in a nutshell what happens in ethylene molecule. Ethylene is, we know that this is CCH2H2, that is CH C2H4. So, there is a double bond here, and this is what is shown there. Well, so if I consider the total internal energy of the molecule to be simplistically, that means consisting of E tans, that is electron transitions, E electrons, that is E transitions is the transitions, then electron transition elective, then vibration transitions, rotational transitions, and nuclear transitions. So, normally electron transitions are determined by UV and X-ray, vibrations are infrared, and are just as I have just told also, and these are different energy levels I have shown you. So, in UV and visible spectroscopy, this is the interaction of the molecules and absorption of proton results in electronic transitions, I have also told. What is most important thing is that these ones are used to detect the presence of chromosphere like dienes, aromatics, or polythenes, or conjugate kettons itself. We will also discuss what is these. Okay. So, there are, as I said, I will discuss about these different electronic states. There are 3 types of electron transition which can happen actually. One is p, s, and n electrons, and transitions involve basically charge transfer, and transition involving d and f electrons are also possible in metal ions like transition metals. Absorptions of these lights like ultraviolet visible radiation, organic and molecular, restricted to certain functional groups like homosphere that contain valent electrons of low electronic excitation energy. That means, if you want to have transitions in the UV visible spectroscopy for p, s, and n electrons, the excitation energy should be as low as possible. Otherwise, because UV and visible are not very high energy, so it will not happen. This is again shown here. This like sigma 2s, sigma from bonding to anti-bonding, pi 2p to pi 2p star bonding to anti-bonding, sigma 2p to sigma 2p star bonding to anti-bonding orbitals. And if I want to show in a detail, this what is shown here. This is the sigma bonding orbital, pi bonding orbital, or n non-bonding orbital, then pi star anti-bonding, sigma star anti-bonding. Energy level increases this way. So, transitions are like this. From n to pi star is this one, which is shown here, left one, or sigma pi to pi star is this one shown there. This can be detected by UV visible. Okay. Okay. Now, you can also have transition like n to pi sigma star, like non-bonding to anti-bonding, or you can have pi bonding orbitals to sigma anti-bonding orbitals, or you can have sigma to pi star. You can have sigma to sigma star. So, and you know that these transitions require different energy levels. So, depending on these energies available, we can basically use different wavelengths of light or UV to have this transition possible. So, that is what I said in a nutshell. In a UV visual spectroscopy, you actually got to know the exact transitions happening from different electronic orbitals, and these are the different electronic orbitals possible. And again, this is shown in detailed manner, okay, so that you can even look at it. This is, I think, this is the nu bar, and this is lambda. So, 100, 200, 300, 400 nanometers up to 800, and this is visible from 400 to 800, and then 400, 200 near ultraviolet, 200 to 100 is far ultraviolet or vacuum UV, which are normally not used in UV visual spectroscopy. So, we will talk about from 200 to about 800 or 700 nanometers, and you can have this kind of transitions in 200 wavelengths. You have a these are actually so pi to pi star, n to sigma star possible, and you have in 300 level is n to sigma pi star, and very high visible range you can have n to pi star. So, therefore, if we use these wavelengths, we can determine these transitions very easily. Now, let me tell you each of these transitions. Sigma to sigma transition, an electron in a bonding s orbital, S is one of these AsP d orbitals, they are in an atom. So, an electron in a bonding orbital S is excited to corresponding anti-Bonding orbital, the energy required is obviously very high, because S is the lowest energy level. So, you have to take it from the S energy state to the anti-bonding state, is very high. So, therefore, in methane, like you have CH4 in a methane saturated compound, only CH bonds are there. So, I can actually write down there are 4 CH bonds in a methane molecule, and these bonds are actually all saturated, you know that, and can only undergo this sigma to sigma star transitions. That means electron can be excited from S bonding orbital and to the anti-bonding orbital, and maximum absorption for this is at about 125 nanometers. So, these transitions are not seen, because 125 is far UV, not seen in the visible spectroscopy range. They have to be used, we have to use far UV or vacuum UV. And if you have a N2 sigma star transition, that is non-bonding to anti-bonding sigma star, saturated compounds like contain atoms like lone pair, non-metal electrons, they are able to these transitions. This transition usually need less energy than the sigma to sigma star. Sigma to sigma star obviously because you are going from bonding to anti-bonding sigma transitions, saturated. They cannot be initiated by light, whose wavelength is in the range of 150 to 250. Number of organic functional groups with N star peaks in the UV regions is very small, because their range is 150 to 250. That range has to come, so therefore it is small. Now, if you want to look at N to pi star or pi to pi transition, they are the most easily detectable in UV visible. Most absorption spectroscopy organic compounds is basically based on the transition from N or pi electrons to the pi star excited state. Transitions fall in the experimentally common regions of spectrum like 200 to 700, that is visible to UV. These transitions are needed in an unsaturated group in the molecule, provide the pi, that is the ethylene. Ethylene has unsaturated this bond, double bond, and it has also pi electrons which can undergo transitions from bonding to anti-bonding. So, these are the things which are called chromosphere. CC double bond, CO double bond, this is ketone, NO double bond, or you can have CX, X can be bromine, iodine. And CC double bond times you will normally have pi to pi star transitions, and like in hexane solvent, this is the maximum wavelength possible. Absorption can happen. You can have N to pi star sigma or N to pi star transitions, pi to pi star at these two wavelengths for ketones. For nitrous group, you can have different wavelength regions, these absorption maxima, and for this kind of CX bonds, you can have N to sigma star or this non-bonding to anti-bonding sigma star or transition, that is at these wavelengths possible. In all cases except nitrous bonds, we use what's called hexane. In this case, we use ethanol as a solvent. And this is this is a table which is obtained from this book Lambert and Forbit, Crooks, Stout, Schubel, Organic Structure Analysis from Macmillan publications. What is showing you these different chromospheres and the present in different compounds, solvent use, absorption maxima, and one can actually molar absorbities values can be calculated from the Lambert Beer's law rather, which again I will discuss. And for those of you who might not have understood exactly what is a sigma bond is basically, suppose you have two nucleus and this is how the electron distribution happens in a sigma bond. Okay, single bonds are usually too high, and it requires very high excitations. We want this to go to the sigma star transition, sigma to sigma star transition, that is from sigma bonding to anti-bonding transitions. This is very high, we have seen that also. So, we need vacuum UV, and then you can have that, this is the anti-bonding. So, you break this bond between them and form this kind of transitions. So, this is low to high from bonding to anti-bonding sigma. Pi is the orbital is like this, you can have electrons distribution in this kind of geometry, and if you want to excite it by using of certain energy, it will go to the anti-bonding state of pi star, where there are different states, different things. This is easily accessible by visible spectroscopy. And non-bonding electrons do not take part any bonds, actually they are neutral energy levels. To give an example, like in a formaldehyde, very classical aldehyde compounds, you can have carbon, there are 2 oxygens and there is a double bond here and carbon. So, this is like this, I can write down. So, there are 2 electrons here, there are 4 electrons here, 2 are bonding and 2 are others, and then an oxygen has 4 electrons. So, we can clearly write this black dots filled, ones are basically sigma, cross are basically pi, and these are actually non-bonding type. So, you can have in this molecule itself, if I apply energy, there are different kind of transitions possible. I hope I have given you enough idea of what kind of transitions. So, in ethylene, if I want to write it down properly, ethylene you can see that this is the pi and this is sigma, and different energy levels I am putting, and these are these sigma pi star and sigma star anti-bonding. And if I apply energy levels, all has the tension probably has happened because there is a double bond between the 2 carbon atoms. So, this chromosphere is CC double bond. So, it can undergo tension from pi to sigma pi star and giving this much of energy, and this happens at this wavelengths. So, these are all known classically, so one can use to determine this very easily. Similarly, in a ketone, these are the non-bonding electrons which I told you, and there is a double bond and there are there is a pi and then other electrons. So, you can have different kind of tension like pi to pi, n to n star, or pi to pi star, sigma to sigma star by putting energy level. And when n to pi star tensions is actually at longer wavelengths, but not as strong as pi to pi star. So, therefore, n to pi star tension is not normally forbidden. In acetone, this n to sigma star tension happens at 188 nanometers and n to pi star happens at 279 nanometers with the molecular absorbability given by this value, which can be calculated or measured. And I can actually go on tell different kinds of bonds. This is saturated carbon-carbon bonds, what you can see. The only possible thing is sigma to sigma star with very high energy, not possible in UV visible spectroscopy. CC single bond pi to pi star is also not possible. The N to sigma star in this case is very weak, so may be possible at 183 UV. And then you can have OH group, that is alcohol, OH alcohol group. You can have sigma to pi to pi star, N to sigma star, N to pi star tensions, so weak. The same thing is possible in this. To give you a ketone situations, you can see that there are spikes in the wavelengths at 188 when you put absorption versus wavelengths and 279. So, these two are telling you 2 kinds of transitions possible. One at 279 is basically corresponding to N to pi star and 188 corresponding to N to sigma star transitions. Well, now these are all qualitative discussions. Now, what we can do is that we can basically use Beer's law to quantify different kinds of absorption. As you know that when light passes through or molecule is passes subject to the light, or a particular wavelength of light is passing through a solution, when the molecules are there, they can undergo transitions which I have shown you. And obviously some light is getting absorbed, some light is absorbed light is used to promote this kind of transitions. So, optical spectrometer basically records the wavelengths at which the absorption happens. Light is also eye is also an optical spectrometer, it also do that same stuff. And then the spectrum which is presented as I shown you in terms of A versus wavelength, absorption versus wavelengths, and it gives you peaks. So, absorption usually ranges from very small value like 0 to 99% possible, and it can be precisely determined by spectrometer. So, because the absorption of a sample is basically proportional to the number of absorbing molecule present in the solutions, the molar concentration basically determines the number of absorbing molecule present in the sample, and then therefore one needs to correct these absorptions by considering different kinds of parameters like operational parameters, and to exactly obtain the amount of light or amount of radiation absorbed by the molecules present in the solutions. The corrected absorption is obviously called as molar light absorbing functions, okay, sorry, molar absorbability, and they can be used to determine to basically this is determined, molar absorbability is determined using this formula which is given here, A by BC, where A is this absorption and B is this path length through which the light is or the radiation is passing through, and C is known as the concentrations. So this can be done. So suppose I will give you an example. If I take isoprene, isoprene is rubber, all of we know this natural level is isoprene, okay, which is obtained from the tree, and it is used for many kinds of purposes. So and you know this isoprene actually in a dilute hexane solutions, if you have like C is equal to 1 to the 4 to the minus 5 moles per liter, and if the path length P is basically 1 centimeter, and then we can use this formula and get sigma to be about 20,000 amount. So, so by knowing this epsilon, so not sigma, epsilon, we can actually quantify the different kinds of absorption behavior by the molecules, and it is can be even formulated by this way. Suppose I0 is the initial radiation, initial intensity of the radiation, and this is this B is this path length, I is the final which is coming out. So I by I0 is di by d0 is basically Kc by dB, or you can say this K is a constant, and then one can get this kind of formula, and the epsilon, which is the molecular absorbability, can be written by K by 2.303, which comes basically from log. And transmission, as I said, can vary from 0 to 100, and opposite is the absorptions. Absorptions can also vary from 0 to 2% in this way. So one can actually get idea. Now depending on the path lengths, obviously if you have 0 100% transmissions, if you have 0.2, so one can get percent transmission versus path length, this kind of behavior or this kind of behavior, and then one can actually use this external standard and calibrate this curve. So this is the absorption, this is the concentration. You can see it follows the linear law where R is very high. So the R is the confidence levels of the fitting, which is almost 99% or 99.86%. So standard addition method is, standard addition must be used whenever you have a matrix, because you have a lot of other factors which determine this absorbability, and so slope of this working curve, a standard made with the distilled water, is different from the same working curve. So therefore there are many ways. How do you prepare the standards? The standards can be prepared in different ways, like this is stock solution which concentration is known, then you can dilute it and get different concentrations, and that's why you can prepare the standards. The concentration volume of the stock solutions should be chosen to increase the concentration of the unknown by about 30% in each flux. That is, this is the known, this is the unknown, so you add unknown quantity, different concentrations, and then add up, make it up to maximum 30%. And this is the response. One can see that if you plot CSA and response, this is straight line, it passes from these 2 points. So using this, one can actually find out this is the unknown concentration Cx. As you know, A is given by sigma Bc, C is this concentration and B is the path length. So we can write down sigma B Cx by Vt, and this is the known, this is the unknown, and this is what is known as K. K is obviously given by sigma epsilon B by Vt, and Vt is the total volume, and so therefore y is equal to Bx, B plus Cx, Ax, A is the KVS, Cs is known, and basically and X is the Cx, and so therefore when A goes to 0, KVx is minus KVCs and Cx is equal to 2. So that is why you have to do. Before I go to the real instrumentation, how the experiments are done, let me show you some spectra. So this is one spectrum, electronic spectrum, basically shown here. You see there is nothing in the visible range, nothing in the visible range in the sense this there is nothing absorbed in the visible range, so 0. One can what has happened is that there are 2 peaks in the UV range for this whatever compounds are used, and they are coming at different values of the lambda, and so the one can actually determine this the epsilon, that is molar absorbidities, by using this 2 different compounds. First of all, one can find out from these peaks what are the exact transitions. So what is normally done is that normally if you want to apply BR's law for quantification, we need to use very small concentrations, and as I said, UV bands are broader than the photoelectronic standard. So, therefore, this is vibration levels are normally superimposed, that is not people say. Well, what solvents normally used for UV like water, or you can use, there is very high epsilon, you can use CH3CN, okay, which has 210, C6H12 is hexane 210, ether 210, very small, we have ethyl alcohol 210, hexane also 210, methyl alcohol 210, dioxane 220. Then you have CH2Cl2 235, CaCl3 245, carbon tetrachloride 265, benzene 280, acetone 300. These are the different energy cutoffs. Okay, so now what you can calculate, can you calculate the UV spectroscopy actually? So, one can actually calculate by looking at the local structure. So, this is suppose the local structure of certain compound nacinol and acidol, and then one can actually calculate the absorption happening. You can see absorption happening at these two wavelengths. One is this is 230, 240, 240, 45, and this is about 275. Similarly, this is another one. This is same molecule. Okay, this is sort of changes the rotation. This is the transition we are talking about it from this to this and this to this here. So, one can determine this spectroscopic things. If you have an orbital involves, like here you have a orbital transitions which is shown here, atoms with molecular orbitals contributed most to the bands, like this one can be considered to be these transitions, this one considered to be these transitions, these are all natinol, and then you can have this transition corresponding to this one, or you can have this transition corresponding to this one corresponding to this molecules going to sigma to pi transitions. So, one can determine that, and quantification also I just told you, so I do not need to discuss. So, let me straight away go to the spectrometer principles or the how the instrumentations are done. Well, as you can see that this is the in a nutshell, this is the schematic picture. What I can tell you that you have basically a reference and a sample. Cuvette is the sample crucibles which is used. Okay. Now, you have a light source like this. You can have light source from UV and light source from visible, and then falls on a mirror, it passes through the slit and then falls on a diffraction grating, passes to another slit. It can be filtered also because you want to use probably the exact wavelengths which is required, and then it can basically go, one of this can basically go to the reference beam, can go to the reference sample, and it will be then focused by the lens 1 to a detector, and intensity will be recorded. Other part you can go to the sample and then falls on the lens, and then it will be focused by the detector and gets the intensity I. And then once you know the absolute value of the intensities, then you can use the Lambert's law, Beer's-Lambert's law to get the value of the molar absorptivity for the particular sample. Well, normally we used quartz as a cuvette. Samples obviously are to be very small concentration, like 10 to the minus 5 molar, and it has to be protected. All these tubes has to be protected from sterilites, which I discussed in the first class why the sterilites are bad, and normally D2 lamp is used for UV and tungsten lamp is basically used for visible, and double beam actually is made makes a different techniques. Now, there are different kinds of instruments can be used. One is fixed wavelength instruments, a scanning wavelength instrument, or diode array instrument. The most recent one is diode array. So, in a fixed wavelength instrument you have LED, light emitting diode as a source. LEDs, there are green LED, blue LED, all kinds of visible LEDs are possible. So, these LEDs actually you can see red, yellow, green and blue. So, these LEDs actually emit a particular light of wavelengths of light, and then it falls on a sample, and no monochromata is needed because LEDs actually emits very precise monochromatic light, and then it falls on a sample, and then whatever getting out are detected by photodiode. This is how the fixed wavelength instrument work. Normally there are 4 LEDs to be used, so the 4 wavelengths can be chosen by this. Now in scanning instrument we do not do that. What we do is that you have tungsten filaments for visible, and you have a D2 lamp, that is deuterium lamp for UV. This is D2O, okay, D2 lamp, and this is the tungsten I showed. So both of them actually comes and passes through the slit, and then you have a monochromator here. How the monochromator works is basically has crystals, basically a Bragg's law. I will tell you how it works. So there are crystals, and then from which you can orient this, scan this, move this one so that it can fall, and when you scan this one, only there is a slit here, so only a particular wavelength will pass through the slits and it will fall on the sample cuvette, and then you have photomultiplier tube which will determine the whatever radiation is coming out. Very simple. So how this monochromator really works? Okay, as I said, there are different lamps can be used. You can use general lamps also, and monochromator basically applies this Bragg's law. Okay, and this is the Bragg's law, n lambda equal to 2d sin theta, d sin I plus sin r, it can be written. It has a angular dispersions given by 2I by T as n by d cos r. R is this basically reflection and I is the incident beam. So many times we write n lambda is 2d sin theta, and sin theta is basically the incident, the angle, but here you can split into like this, d sin I plus d sin r. So that is nothing. If r and I are different, then one has to write like this. And resolution is obviously given by lambda by delta lambda, okay, or NaN is extended, can be actually extended by concave mirrors in these monochromators. This is what is done here. You have these crystals which are sitting there, they are actually reflecting the lights at different directions. So if you scan it out, only a fixed wavelength will pass through this cap. And holders, sample holders, this is also very important for instrumental purpose. You have a visible, for visible use plastic or glass, for UV you must use quartz. These are all examples. You can have single beam, double beam. Normally single beams are used, double beams are normally used, but single beam can be used, but we have a source flicker. The last one is diode array instruments, in which you have both the lamps, tungsten and the deuterium, for the deuterium lamps for the UV and tungsten for the visible, and then it goes to a slit and falls in a mirror, and mirror focuses it onto the sample, and then this falls on a monochromator. This is opposite to what you have seen in case of the techniques, scanning techniques, and then this by this monochromator actually moves, and then different wavelengths of lights falls on 32/8 detectors, which each one is a 320 detectors, each one is a diode, and diodes measure the amount of the radiation which is coming out. Well, so there are advantage disadvantage for the both scanning and the diode array. Scanning has low spectral resolutions, high spectral resolution, sorry, lambda by lambda, delta lambda is very high, but it has a long data acquisition time, which can be several minutes. That's sometime may be problem for different solutions, and it has a low throughput. So diode array has a very fast acquisition time, because it is diode array is basically determine the intensity of this radiation which is coming at different wavelengths after it passes to the sample, and normally it's couple of seconds in comparison to several minutes, and is compatible with online that is computer compatibility is there, a very high throughputs, there is no slits, and but it has problem is very low resolutions. So if you want to go for high resolution, you have to use scanning instruments. If you want to go for fast and the what's called high throughput instruments, you have to go for diode array. Normally people have both in the labs normally, and this is the extended view of diode array I am showing you. These are the 328 diodes which are laid there, and after the sample radiation comes from the sample, it is detected there. Well, so that's all. In the next class I will show you some more spectra from the UV visible results in my lab, and some of the things which I gathered from the literature, and then we move on to the next techniques, that is photoluminescence.